Hi to everybody. Uh, we are happy to organize this second session of the GGI Young Researcher Seminars. And today we are glad to have Níckolas de Aguiar Alves as our second speaker. I hope I read it correctly. And he will talk to us about why do things fall, an introduction to quantum field theory in curved space-time. So Níckolas, when you want, feel free to start.
Thank you very much. The title of the seminar is as it is because I really like how in theoretical physics it is easy to get to very deep questions about the universe. So you have, for example, what are things made of? I'm going to be right quite a bunch because otherwise I'm going to speak too fast. What are things made of? Or why does time move forward? How did the universe begin? And of course, why do things fall? And something that I really like about these questions is because even a toddler could ask them in principle, but still we don't really have sufficient answers for them in theoretical physics. So if you bring, for example, what are things made of and why do things fall, which are my two favorites out of these ones. Then we have been trying to answer them for at least a few millennia. For the ancient Greeks already had some tries at this. They would say that things are made of 5 elements, which would be fire, earth, water, air, and ether, while things would fall because that's their natural motion. Nowadays, however, we would answer them very differently. We would say that things are made of the standard model, while things fall due to general relativity, which are our best theories for each of these questions nowadays. And what I find funny about this is because the Aristotelian version, in which you say there are 5 elements and they fall due to their natural motion, you have these two theories working together and they match each other. However, if you bring the SM and GR together, they appear to be at conflict in the sense that general relativity is a classical theory, it knows only of classical things, while the standard model is a quantum theory that has a completely different way, a completely different language of speaking what things are made of. So, in other words, we don't really know why the things that make everything up fall. So while we know why a ball falls, for example, or we can give a good description for why a ball falls, we don't really know why or how an electron falls within general relativity. However, there is a way, which is a quite natural way, of trying to understand these deeper questions without going too far and without making bold assumptions about what exactly we are doing. And here's the idea. In general relativity, what we have is the following equation, the Einstein equations, which describe that space-time tells matter how to curve. GAB is the Einstein tensor, which is a measure of how exactly the space-time is curved. And TAB is the stress energy tensor, which tells us what is the matter content of the space-time. So space-time tells matter how to move, while matter tells space-time how to curve. And this is the description given by GR. However, we can make an update to this so that we can now understand a little bit about how quantum things fall, so how quantum fields fall. And to do so, we could add, pictorially only, another term to this equation, which would be something like the expectation value of a quantum energy tensor. And this is what we call Q of TCS, with only one arrow. So we let space-time determine how quantum fields move. However, I am not adding here another arrow for quantum matter to tell how space-time curves, because that would be semi-classical gravity, which is way more complicated. And we're making this compromise of letting only the classical matter tell how space-time curve, because otherwise it would be too difficult to deal with the equations. And in no place am I assuming that gravity is quantum in here. It might be, but we are doing a simplifying assumption in which we treat gravity as classical so that we can get to a more simple theory and still understand how quantum phenomena and gravity correlate to each other and interact with each other. My favorite example of how exactly this setup, which is known as quantum field theory in curved spacetime, works is actually in Minkowski spacetime. It is known as the Unru effect. And to illustrate it, I will consider first inertial observers, but we'll also consider what happens to accelerating observers, which are non-inertial. And we'll already illustrate some of the features of quantum field theory in curved spacetime, even though we are in flat spacetime. So we consider a Klein-Gordon field. So it obeys the equations of motion given by this. I'm using the minus plus 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 signature, which tells us that for inertial observers and for a massless field, which I take for simplicity, and in 1+1 dimensions, which I also take for simplicity, we have the equations of motion as being simply a wave equation. I'm making these assumptions in here simply because this allows me to do the calculations more easily. But we could also consider a massive field in 4 dimensions, for example, and have similar results, although the calculations would be far more complicated. So we have this expression here. By introducing different coordinates, we can introduce the retarded time t minus x and the advanced time t plus x. This gives us a different equation, which is just going to be the same equation actually, but in order coordinates will give us the second derivative of phi with respect to u and v equals 0. And this is interesting because it allows us to solve it more easily and find that the field is given by some function, the classical field, by some function fl of the of the right moving modes, which are functions of u only, and fl, which are functions of v only. And we could rewrite this as t minus x plus t plus x. So far, this is only a solution to the wave equation, the general solution to the wave equation. Now, we can start moving toward the quantum theory. A way to do so is to first decompose the field into harmonic oscillators, which is equivalent to say that we're going to make a Fourier transform of the field, and we're going to get something of this form. We have some coefficients, a omega, the solutions e to the minus I omega t minus x. We are integrating over omega, and I'm going to add a factor of 2 omega in here to normalize these a omega coefficients. This is for the right moving side, and we also have the left moving modes in here, which are just the same. It is convenient to rewrite this in a slightly different manner, which is going to be from 0 to infinity, a omega e to the minus I omega t minus x plus a minus omega e to the plus I omega t minus x d omega square root of t of 2 omega plus left moving modes. This is just a way of rewriting the Fourier transform. I just took the negative modes and wrote them as if they were positive in here. And this is interesting because now, for a scalar real field, sorry, I can just rewrite this as the same thing. A omega minus I, t minus x, plus a omega star, which is the condition for the field to be real, e plus omega t minus x, d omega plus dot moving. Now this is for a classical field. In order to quantize this field, we can just impose that these coefficients a omega and a omega star should be operators instead of simply numbers. And we impose the condition that a hat omega, the operator a omega, and a hat omega dagger, which is the operator version of a omega star, omega prime, sorry, should be given by a Dirac delta. The commutator of them should be given by a Dirac delta of omega minus omega prime. And in this way, we have the quantum field as being given by, let me just find the region. As being given by this expression. With a hat, and the star becomes a dagger. Now this is the way we do quantum field theory for an inertial observer. Now we have the field operator, and we can start acting with it or with the operators, with the ladder operators, a omega and a omega dagger, in whichever way we sound it fits, in order to obtain results for an inertial observer for a free field. However, it is interesting now to wonder what happens for an accelerating observer. And to do so, we must describe how exactly this accelerated observer moves and decompose with respect not to inertial time, which is what we did here, this t and this Fourier transform that we took was with respect to inertial time, but rather we want to do now a similar description by using the proper time of an accelerated observer. So to do so, we begin by describing how exactly the accelerated observer moves, and it turns out that they follow let me write with mu because I find it's more understandable. They move alongside this killing field, which is a time translation symmetry field, b mu, which is given by some factor a, which is a constant, times x, ddt mu, plus t, ddx mu. And this is the killing field. This is actually the boost killing field. So it is the symmetry, the generator of boost translations in flat spacetime. If you follow this vector field along Minkowski spacetime, you have here the t equals x line, you have here the t equals minus x line. If you follow this field, you're going to find yourself following these trajectories in here. They go up in here, they go down in here, they go, I think, right in here, they go left in here. So you see that they are time-like, they follow time-like curves when you are in this right wedge, which is called the right Hindler wedge. And when you are in this left wedge, which is the left Hindler wedge. We're going to focus on the right Hindler wedge, which is just common in the literature, but the same analysis goes in the left Hindler wedge if you just change the sign of the field so that it moves forward in time. And by taking then appropriate coordinates, we can use the following coordinates to make the description more easy. We pick that constant A and make this following coordinate transformation. Phi, cos, eta. And these coordinates are interesting because of two things. First, d mu becomes now simply d eta mu. And hence, eta is just the proper time for the accelerating observer. Furthermore, the accelerated observer is going to simply sit, these are called radar coordinates, by the way. And the accelerated observer is going to simply sit at psi equals 0, and its proper time is going to be given by eta. The line element in this coordinates becomes ds2 equals e to the 2a psi minus d eta 2 plus d psi 2. So I chose this coordinates also because the line element in this coordinates becomes clearly conformally flat, which makes the analysis more simple to perform. And in this coordinates then, we're going to get, once again, if we perform those calculations in which this would be the equation of movement, in this coordinates, we also get a wave equation. And hence the solution in accelerated coordinates is going to be given by some function that is right moving and takes eta minus xi as an argument, plus some function that is left moving and takes eta plus psi as an argument. Now, we can also define this as being, to find this result, we can also define u equals eta minus xi, and v equals eta plus xi, and the calculation goes just as in the inertial case. And what is interesting with this new coordinates in here is that if you pick the line element in these new coordinates, you have with those previous new coordinates, little u and little v, it is given by minus du dv, while for this large u and v, the new coordinates are going to be given by 2a, it's v minus u, du dv. Now, by looking at this equation, you can see that the absence of terms such as du2 or dv2 imply the fact that they are not there, imply that u is a function of only u and v is a function of only v, or the opposite. They can't be functions of both at the same time. So u, v is not possible, it's only u. or only v. It can be shown that the correct answer is only u and only v. So u is a function of u and v is a function of v, which means then that left moving or right moving is the same for inertial and accelerated. Hence, we can just analyze right moving and treat left moving the same way, regardless of whether we are dealing with the inertial or the accelerated observer. They both agree on what is left moving and on what is right moving. Hence, we'll focus simply on right moving from here onward. And I'm just going to keep adding that small l at the end of our equation. The correct expression for u and v in terms of big U and big V can be shown to be some references for this can be shown to be that I'm talking about now and then are the books by Bukhanov and Vinitsky. Or Ward, or Barrow and Davis, which is another possibility. Whichever is your preferred. Bukhanov and Vinitsky is one of the simplest approaches that I know. And most of my discussion here is following Bukhanov and Vinitsky. And it can be shown that u of u is equal to e to the minus au, there's a minus in here, over a, y of v is equal to plus e to minus av over a. Using this discussion of how similar the accelerated and inertial descriptions are, we can also decompose the field as for an accelerated observer, and it would have the appearance of this expression, which we also go from 0 to infinity. We do now have coefficients b omega e to the minus I omega t minus x plus b omega dagger e to the plus I omega eta minus psi eta plus psi d omega. Let me use it a larger omega here just to make a difference. The omega over 2 omega plus left moving. So you can have this description or the inertial description. Both of them work, at least while we are in the right Handler wedge. And the reason we must be in the right Brindle wedge is because these coordinates that we're using, psi and eta, are defined only in this region. This can be seen because of the ranges of x and t in this expression for psi and eta ranging from minus infinity to plus infinity. You see that x is always going to be positive, for example, because cosh is always positive. So we are in this situation, we have these two descriptions, and of course, I'm also normalizing so that b omega and b omega hat are given by d omega minus omega prime. There's a prime in here. B omega dagger, not b omega hat. And we can now try to relate these two descriptions. So for example, if you ask an inertial observer how many particles are there in the spacetime, he's going to look at this expression here A omega dagger, A omega, and it's going to see 0 because A omega annihilates the vacuum. So the calculation you have in here is going to be 0, 0. You know then that this is going to be 0 times the creation operator, hence it is 0. However, for an accelerated observer, we have B omega acting on 0. We don't know a priori whether this is 0 or not. We don't know what it is, how exactly it is evaluated. But we know that somehow it must relate to some expression involving A's omegas instead of B omegas. I mean, yeah, I should always remember that it is capital omega. Things they must be related somehow. It must be possible to write B omega as a combination of A omegas and A omega daggers, where alpha and beta are coefficients. This is true because somehow we know that phi is given by both that expression in terms of A's and this expression in terms of B's, so somehow they must be related to each other. And the operators in both expressions are only A's or B's, hence the operators must be related to each other in some way. And the coefficients that we use in here are going to be called alpha and beta. In order to keep the normalization that B omega has,
Là,
B omega
je commence à asseoir certaines bases que j'ai un peu négligées, comme la
Sorry, I
mécanique
couldn't
quantique,
understand that.
mécanique quantique et la théorie quantique des champs, la théorie qui va après. Quoi? Ce que j'ai dit là.
Okay, I'm going to continue. So that B omega dagger equals, let me select this. Still, the delta, it is going to be necessary that this coefficient satisfies something. It can be shown that actually they must satisfy. This is a direct calculation. It's just throwing in this in here. There's a prime in here, minus beta omega prime omega, d omega equals z omega minus omega prime. So you have this normalization condition. And I'm going to notice also, for future reference, that in the case omega and omega prime, big omega and big omega prime are the same. This leads to a omega omega minus b omega omega, the omega equals delta 0. This will be relevant later. In any case, these two equations in here are known as a Bogoliubov transformation. They are also very useful in condensed matter physics. And they are just changing the perspective we have on the quantum field. So they relate the perspective of an inertial observer with the perspective of an accelerated observer. Using these equations and the decomposition that we have right here, we can just insert this equation into this equation and compare with the decomposition that we had fairly early on in terms of phase, because we're just going to get a mixture of phase in there. So it's going to be something like we have the field is given by 1 over 2 pi. Now we're going to have, instead of B, we're going to have A omega A minus B omega A dagger times e to the minus big omega eta minus psi plus blah blah blah. And comparing these things with this expression and the original expression in terms of phase, we find that e to the minus omega little u over square root of omega, which appears near the differential. And now remember that little u is t minus x, is going to be given by an integral from 0 to infinity of alpha omega omega e to the minus I big omega big U minus B star omega omega e to the plus big omega big U d omega over omega square root of omega. Using this expression, we can now notice that the integral, and this is now we are now getting to a few fairly technical steps, but it's just integrating over and over again. That 1 over square root of omega e to the minus omega u plus or minus I omega prime big U du is going to be given by integral from minus infinity to plus infinity, integral from 0 to infinity of alpha omega e to the minus I omega minus plus, because there's a minus in here, omega prime U plus, which is going to be the same thing, similar thing, but for B star, and there's also this coefficient at the end. Integrating over du is going to give us a Dirac delta, and hence we get 2 pi integral from 0 to infinity of alpha omega omega d omega minus plus omega prime minus b omega star omega d omega plus minus omega prime, all of this times the omega over square root omega, which now is just an integration of a Dirac delta, so we just get to 2 pi over omega prime a plus minus omega prime omega minus b star minus plus omega prime omega. It can be shown that alpha plus minus omega omega is actually equal to minus b star minus plus omega omega. Using this in this equation, and this expression in here, we find that A omega omega equals to 1 over 4 pi omega over omega minus infinity plus infinity e to the minus I u omega plus I omega u du while beta omega omega is going to be given by nearly the same thing, with the difference that it actually has a plus in here. With some manipulation, and well, by some I mean a lot, it can be shown that A omega omega squared is actually equal to e to the 2 pi omega over a b omega omega squared. This is a problem in Mokhanov and Janitsky, but they also give some steps to how to show this. And now we get to the most important results, which now, for an accelerated observer, number of particles observed is equal to the expectation value of particle, or number of particles observed, going to be given by b omega dagger b omega, which we can rewrite using the Bogoliubov transformation. After we consider that the vacuum annihilates, and the vacuum is annihilated by the A omegas, we find that this expression is equal to B omega star omega prime B omega omega times A omega prime A omega dagger D omega prime, which does not vanish. So after we consider the Bogoliubov transformation, we end up with an expression that does not vanish when you consider the number of particles. Instead, what we're going to get in here is going to be given by, let me just copy this expression. Let's start here. And this expression becomes a delta omega minus omega prime. So what we get in the end of the day is just an integral of b omega squared d omega. Now, since we know that a omega squared minus b omega squared d omega equals delta zero, and we know that this is merely e to the 2 pi omega over a minus 1 times b omega. We find that the expectation value of the number of particles is going to be given by delta 0 divided by e to the 2 pi omega over a minus 1. This delta 0 is merely an expression for the volume of spacetime. So the expectation value of particles per volume is going to be given by little n omega, which is 1 over e to pi omega over a minus 1, which is a Bose-Einstein distribution at temperature T equals A over 2 pi. Hence, for the accelerated observer, while the inertial observer sees nothing, sees no particles at all, the accelerated observer does see particles, and furthermore, they see it with a thermal distribution proportional to their acceleration. This is the Unru effect. It is an astonishing prediction that the notion of particle is actually not fundamental in quantum field theory, but rather it is only an observer-dependent construction, and gives this astonishing result in which, depending on whether you are accelerated or inertial, you might or not see particles and you might or not see thermal radiation. And before I continue, I think this is a good place to stop for questions in case there are any. And next I'm going to move on to the Hawking effect, which is then in true curved spacetime, although I will not do the full calculations. So are there any questions? Okay, I believe not. So next, I'm going to move on to the Hawking effect. Which is actually the first effect to have been predicted in quantum field theory for spacetime, at least. No, not necessarily the first, because there was a QFTCS started with cosmology, and I'm not really expert in cosmological QFTCS. But within black holes, the Hawking effect was the first effect. Black holes and Unru effect things. The Unru effect arises as a manner of trying to understand the Hawking effect. So the Unru effect was derived by focusing mainly on how exactly big U and little u connected, and big V and little v connected, on this region, in which t equals x and t equals minus x. This is known as a bifurcated Killing horizon. Killing horizon. Killing means symmetry in general relativity, and bifurcated Killing horizon means that in here you have the symmetries and at this horizon, at this X structure, they become null, they become like. And it's bifurcated because it is bifurcating at this point. So you have this X structure. Now, a different spacetime, which also presents a bifurcated Killing horizon, and the presence of a bifurcated Killing horizon always implies the Unru effect, is a short spacetime. It is represented pictorially by this Penrose diagram, which you have here the X structure. And how to read this. In here, in this diagram, light moves always at a 45-degree angle. So light at 45 degree. This is the black hole region. This is our universe. This is a white hole region, which appears in an eternal black hole spacetime. And this is sort of a parallel universe. This is a solution full of symmetry, so it is actually not really physical, but rather an approximation to physical black holes. So you can start here in our universe and move within light speed and fall within the black hole, where you now cannot escape unless you move faster than light. And hence your destiny is to just fall in the singularity, which is this zigzag line. The fact that you have this cross in here also leads to the Unru effect, this time for temperature given by the Hawking temperature, which is given by with units. I didn't put the units in the Unru effect, but I'm going to put it for the Hawking effect. 8 pi g m kb. A common argument for why this happens is that near the black hole you are accelerating if you are staying static. So you have the black hole in here and just standing in place, and you are accelerating backwards. And hence the Unru effect applies and you have this result. I don't like this argument. This gives some intuition for why this must be true, and this is pretty much the acceleration that you need in order to keep away from the black hole in some sense. Over 2 pi. However, there is a detail in here that is what makes me dislike this argument, which is the fact that it really depends on the specifics of the spacetime and on the quantum state of the field. So this is the Unru effect in curved spacetime. But another possibility, instead of considering an eternal black hole, would be for us to pick a different case in which you start with a star, and this star eventually collapses into a black hole. And you have here the black hole horizon. Now, this situation can be was shown by Unru to be analogous to having a full eternal black hole, but with different boundary conditions. So we are going to have here the horizon, and what happens is now that you're focused only on this region outside the star, which is this yellow region. So you no longer have the complete horizon, you have only a piece of it. You're only focused on this piece. And now the quantum states that you can consider are different, because previously, when you're dealing with this horizon, you have a single interesting quantum state, which is called the Hartle-Hawking vacuum. It is a quantum state which is normalizable, renormalizable everywhere, in the sense that if you try to calculate the renormalized stress energy tensor, it is going to be possible. And furthermore, it must be static or stationary everywhere, since this spacetime is stationary. And you can get that with a single state, and the state is always global. So there is a single state that satisfies all of these properties of being stationary and of not being non-renormalizable anywhere, which is the Hartle-Hawking vacuum. Now, in this different case, we don't really we can't really use the Hartle-Hawking vacuum because there's no white hole to emit modes outward. Where in the physical spacetime, which is this one, this simply does not exist. So we must use a different vacuum, which now can be non-normalizable in this purple line that I'm drawing right now. This is known as the Unru vacuum. And it is a vacuum for this sort of spacetime. You also have, in this case, a Hawking temperature, so you're also gonna have this expression, but there is a difference. In this spacetime, you're going to have a Hawking temperature for modes coming in from the black hole, so they coming in from this region, but also from modes coming in from infinity. So you actually are not feeling that the black hole is hot, you're feeling that everywhere around you is hot. While in this different scenario, in the Unru vacuum, what you get actually is only thermal modes coming from the black hole, and hence you feel that the black hole is hot, not that space-time around you is hot. And this is known as the Hawking effect. It's a little bit counterintuitive. The Unru effect happens with the Hartle-Hawking vacuum, and the Hawking effect occurs with the Unru vacuum. but it is what it is. And this is called the Hawking effect. So what you have, in fact, is a star collapse into a black hole. And what you find is that after the star cools down, and after the black hole cools down and gets to a stationary state, it's actually going to emit a radiation in a thermal spectrum, which is what we call the Hawking effect. It's probably the main effect of QRTCS. It can be understood, both the Hawking effect and the Unru effect can be understood in terms of thinking that particles are actually related to those energy modes decompositions that we did. So they're related to what exactly. So let me go back a little bit. One of those decompositions. So in here, for example, what is called a particle is whatever is created by this guy in here, and that is related to what I call positive energy or negative energy. Sorry, actually this negative energy and this is positive energy. And these relations of what is positive and negative energy is what actually gives me whether I'm creating or annihilating a particle. Now, what is interesting is that if you pick different observers or different moments in our space-time, you might have different notions of time, and thus, by Nitto's theorem, you have different notions of energy, and with different notions of energy, you have different notions of particles. Hence, what happens here in the Hawking effect is that you start with a star. This star eventually is going to collapse. At this initial moment, you see no particles. Eventually, the star collapses to a black hole. Let me draw this in purple. And it eventually settles down. At this moment, you have a different notion of energy. And there's a different notion of particles. And hence, you see particles, because now what you call particle has changed since the beginning of the process. At last, the other situation in structured spacetime that I'd like to discuss is the so-called Bohr vacuum, which happens when you have a star that does not collapse to a black hole. Because one of the things that I find annoying about that argument in which you just use, yeah, I had drawing here, but in which you just use acceleration outside a spherical body to derive the Hawking effect, is that in principle it should also apply to Earth, but we do not see particles being emitted by Earth in a thermal spectrum. And the reason is, of course, there is a different vacuum in here. So for this case, what we have is now a vacuum, a quantum state that should not pick any of those horizons. So there should not be any modes falling into a horizon or coming from a horizon. And as a consequence, the vacuum state can be and should be divergent in both of these purple lines that I'm drawing here. And this is known as the Bohr vacuum. It is not admissible in a black hole spacetime, but it is admissible and it is necessary in a star spacetime, because that's when you actually get this sort of structure in which you are not seeing the horizon because it does not exist. And in this situation, now we don't have radiation incoming from infinity. We do not have radiation incoming from the black hole because there's no black hole, and hence we get a temperature 0. And this explains why we can see we get to predict radiation coming from black holes, but not really from planets or stars, at least not due to quantum effects alone. And this is the point in which I stop. I now hope I have given some light into what is quantum theoretical spacetime. Its most purposes are not really to try to quantize gravity or anything like that. It is rather to give this tool in which you can see how quantum effects and gravity work together without having to make any assumptions about what happens on the Planck scale or any other things similar to that. You only deal with what is happening at very low energy scales, at very low curvature scales, actually, sorry. And hence you can study gravity and quantum mechanics together in a very conservative setup. And I think that's it. Are there any questions?
Are there any questions from the audience?
Sorry, I heard something, but I'm not hearing it right now.
So if there are no questions, we can thank our speaker for the very nice talk.
Thank you.
And see you for the next session for the GGI lectures. So we thank Níckolas for the very nice talk.
Thank you.
And for the very clear explanations about this Unru effect and Hawking effect. So thank you very much. And so thank you guys for following this session, and see you next time. Bye.